Very good morning to one and all again here. In line with the discussion on AGC in interconnected area, we were continuing to understand the role of primary ALFC and its failures when two areas are interconnected by a tie line, trying to deliver the change in loads of area 1 and area 2 respectively. Both the areas were found or they were responding for the change in load. That was not a desirable feature, and that was solved by adding supplementary loop to the old control system. It means that was having a primary loop which was correcting the requirement of change in load by the two areas in common operation respectively at both the ends. So seeing to that, by adding a loop, additional loop to the area 1, area 2, having configured the parameter called as is. This was the screen we have seen. Having added new loop to that, configuring it as an area control error, having an integral controller incorporated, which will act to change the set point of a respective area so that the respective area on whose change of load in that area will only respond for the generation. That was the advantage we have seen by having incorporated supplementary loop to the existing ALFC's primary loop in multi-area system, which was constructed very simple. We had earlier interfaced interconnection between area 1 area 2 as delta P12 and exchanged power, and a primary loop in area 1, primary loop in area 2, where P reference was set earlier and left, and P reference 2 was set earlier and left. Now, due to the interconnected mode of operation, to see to it that whenever there is a change in load in area 2 which cause a change in frequency, let the area 2's generation only work to overcome that frequency deviation. That was the objective with which supplementary loop was focused around the first existing primary loop, and that made a feedback path of delta omega, means the frequency deviation, with the area composite frequency bias beta 2 as well as beta 1 in the first area, feeding it to the summing block along with the exchanging mismatch power as a signal called as area control error, respectively AS2 in area 2, respectively AS1 in area 1, which was input to the integral controller. This error need to be 0. When an error is 0, whatever is the set point available for the primary control loop is satisfying the requirement and matching the requirement such that error delta omega respectively is under the control. Whenever this ACE is not 0, this integral controller will amplify this error by a gain factor and integral of this accumulated error is taken as a set point change to the respective area. So reference point is shifted so that that new point will be active on the governor and mechanism for the primary loop. This way, this ACE become a stimulus for the integral controller, and integral controller interchange the set point of the area, and set point accordingly change the wall position, mechanical input, and address the requirement of the load in that respective area. Similar controlling concept is incorporated in the either of the areas. This is how the vision of supplementary loop was come into picture, to see to it that a change in area load has to be addressed in its own area only. That was the concept. Then in line with this, we began how is that choice factor, bias factor come into picture. So AS become a basic control parameter for the interconnected operation of corporations for exchange of power using complete ALFC, having primary and secondary loops functioning. So that was coined as let AS1, AS2 be the the equations concerned to the area 1, area 2, which is given as a gain K1 and delta P12, the exchanging power among the corporation, which is infinitesimally small change in power, plus beta 1, or you can pronounce B1, beta 1 into delta omega. It should be equal to 0. because AS1 is 0, the controlling area 1 is in steady state. It means ACE is not causing any stimulus to the integral controller. Whatever was a speed set point already set earlier to the action is working fine. That is what we can view from this. Then AS2 is again given as K2, a gain of that area to controller delta P21. And we are very sure delta P12 and delta P21 are opposite to each other, plus beta 2 into delta omega, which would be 0. And having viewed these two equations are governing equation for our interconnected mode of operation using supplementary control to the existing primary controller. When a change in area 1 load is considered, we have studied this equation. Delta omega is nothing but frequency deviation is due to the change in load 1 is written as minus delta PL1 divided by beta 1 plus beta 2. And power exchanged among those corporations, delta P12 infinitesimally small power exchanged, because of which deviation is noticed, is given by delta PL1 into composite frequency bias of the neighbor area divided by composite frequency responses in the denominator added. This was the derivation we have seen in the load change in area 1 only, load change in area 2 only, load change in both the area. They were the three sub cases. From the first case, it is being drawn. Letting K1 equal to K2, gains are same, and beta B1 equal to beta 1, B2 equal to beta 2, like that. If I substitute in these equations, what I will be going to get is, suppose load change is in area 1. What is the intention to show you is, when load change is in area 1, I would express AS must be non-zero in area 1 and AS of area 2 should be 0. It should not compel the controller in the area 2, because load change is in area 1. Area 1 is responsible to work for that. To show that how is that AS act on the area, we can understand by inputting these datas. These datas of K1, K2 equal to 1, beta 1 equal to B1, or B1 equal to beta 1, beta 2 equal to nothing, B2 equal to beta 2. If I locate, I will be able to get from this first equation, AS1 turns to be minus delta PL1, and AS2 in the numerator, it cancels off. It makes the 0. What do you understand from this? AS1 is minus delta PL1, AS2 is 0. I go back to a diagram here. When AS1 is minus delta P1, that is nothing but delta PL1 available here. That is a change in load experience in area 1, which is reflected at the AS of the area 1, which is causing the integral controller to function and make the set point change. So other way, AS of the area 2 is made 0. It means it is not triggering the controller. It is not making the controller to function to change the set point. It means it is in status quo. Whatever was there, with which it is functioning. That is because there is no demand from the area 2. It was already satisfied. Steady state is attained in the area 2. Only load change in area 1 is considered. Then that is causing a deviation in frequency. No doubt both are experiencing the change in frequency. But who is responsible to control this change in load, change in frequency deviation? That is put on AS1. That is area 1 has to concentrate that. Therefore, that is the use of the supplementary control and choice of bias factor using the AS signal. In the energy control center, whenever we find computer control of generation and exchange of power among the corporation, AS is the signal. Depending upon the AS value of a corporation 1, 2, 3, we can understand who is selling the power, who is borrowing the power with a time slice, at what time, how much quantity by value. All these things are characterized by AS only. It is observed by central controlling agency, commonly set for supervision. So for them, AS become important aspect. In that due respect, today what we are viewing, if at all area 1 experience a load change, let area 1 only work for that. The other way, if AS2 is to be non-zero, then what is the meaning of that? AS2 is to be non-zero means what? This deviation shall be due to load in delta PL2. That time, what is delta P21? We have to write here. Using these two equations in the respective, I can definitely get similar representations. AS of 1 shall go beta 1 here, minus cancels off, which becomes 0 here. and here it becomes beta 1 and beta 2 as delta PL2 itself. It means AS2 will turn out as delta PL2, AS1 turn out as 0. What it indicates? Whenever there is a change in load in area 2, AS of that area is non-zero. The other areas AS goes 0, which should not respond for the change in load of area 2. That's what in the previous diagram, if I say there is a change in load in this area 2 and there is no additional demand side by side, it was already met, you can say. Due to the step change over here, deviation is noticed, both will experience, and AS of 1 will not make any correction for that. Only AS2 is reflecting the change in frequency due to change in load. Therefore, controller around this area have to work around that to make the AS0 or frequency deviation under the control. That is the meaning of choice of bias factor and role of AS in that. In general, we know that AS of any quantity, when we saw this, what is this? AS of a control area, how we define it? AS of a control area in general is actual tile and power flow from the control area. What is going on? Measure it. Minus what is actually committed, scheduled, plus 10 times the frequency composite bias of that area into deviation. So F actual minus F naught basic frequency. This is what the basic understanding of area control error we got in the very earlier discussion of the control system. It means such a AS value have to be taken care. So Ti, TSI inside a bracket minus 10 times beta I, Fi, Fsi. These keywords were mentioned here. Ti is the net actual tile and interchange from area I, which is right now going out. Add it up and show that. And Si is the schedule, like a P schedule. And Bi is the frequency bias, composite frequency bias of that. And Fi is the frequency actual, and Fsi is the schedule. Whatever the keyword I was speaking, they were the outgoing power through the tie line, scheduled power, and area gained Bi with a 10 multiplier for the cancellation of the 0.1, and the actual frequency and scheduled frequency. So on that base, usually AS is written. So this AS controls the interconnected operations of the generations like this way. Now viewing this, when we go to a numerical problem, so how AS become important aspect for us to understand. Let us take some problem which are this problem is from K. Umarov itself. The data of two area system are given by area 1 is PG1, and that is a load 1000 megawatt, and group of that is 0.015, and area frequency sensitive loads D1 is 0 and D2 is also 0, R2 is mentioned and 0.0015, and PL2 PG2 equal to PL2 at 10,000 megawatt load. An increase of 10 megawatt take place in area 1. See the area 1 is experiencing a change in load. Determine the change in frequency, AS, and the appropriate control action. Here, this looks like an old conventional problem. Earlier, such problems we have seen, but we haven't worked on the concept of AS. We worked out such that what is the frequency deviation experience for such a shift in load? What is the new frequency? What is the share of generator 1, generator 2? That was the area we have worked. But in this problem, after having understood area frequency bias, how AS become an important control parameter for interconnected operations with complete ALFC. This is what we have to view with the complete ALFC, primary and secondary loops. Then we have to work very similar, but view eccentric at the final. So therefore, we know that from the area 1, area 2 perspective. Hope I am audible to you all. Hope I am audible to you all.
Yes, sir.
Yes, sir.
Okay, thank you. So delta PM1, from writing the total mechanical energy from the first area perspective, mechanical energy which is set up in the turbine mechanics like that is delta PL1, load change in that area, load change with respect to frequency deviation D1 delta omega 1, plus what is that to be exchanged from area 1 to area 2. So this is with respect to mechanical energy balance at area 1 is delta PM1 equal to delta PL1, what is the actual load change, plus what is to be exchanged from area 1 to area 2, plus the frequency sensitive load in that area 1. This is called energy balance here, which is rewritten as delta PL1 plus delta P12 because D1 is 0 here. So this is how mechanical balance, this was viewed this way. In this table we can see this is what I am speaking here. Delta PM1 is what? Delta PL1 and delta P12. This area I am trying to write energy balance. What is the power? What is the demand? What is the exchange power? This situation I am writing as this problem here. Okay. Delta PM1 is delta PL1. What is the change in load in that area? Plus what is being exchanged among the corporations. Similarly, from energy corporation 2 perspective, delta PM2 is similarly delta PL2, its standard load, its exchange power. You can see here delta P12, now it is delta P21. These two are opposite to each other. I can write here minus delta P12. If I write in terms of P12, I should write minus here. But I have written from a viewpoint 2, and it is delta P21. And sensitive loads in the area 2 for the frequency, D2 delta omega 2. As good, D2 is also mentioned 0 here. Then this gets simplified as delta P12 because there is no change in load, because the load changes in only area 1. Hence, this all together turns into delta P21, nothing but delta P1 only from this perspective. Whatever is getting is only exchange to neighbor area. Now, when these two areas are interconnected and a step change of load is experienced, it is quite natural to experience a drop in frequency immediately after the loading. Due to that, let delta omega be the change in frequency. Frequency deviation we call. It is same as deviation experienced from area 1 and deviation experienced from area 2 perspective, because they are connected in parallel. Let it be common delta omega like that. And from the droop representation of the generating or governor generator characteristics, what I can write delta PM1 and delta omega and R. I have what is droop? Droop is delta omega by delta P. So if I take this R other side, delta PM in the denominator, it becomes delta omega or delta F divided by delta P, share of that area, equal to droop. According to the droop, there will be a proportionate pickup in the mechanical parts of the generating and turbine mechanisms. So therefore, delta PM1, what is that mechanical energy balance being taken here is delta PM1 is the deviation experienced by that area, delta omega 1 divided by R1 negative, because the negative droop. So therefore, which is minus 1 by R1 into delta omega 1. And another generating area perspective, delta PM2 is again minus delta omega 2 by R2. No doubt, delta omega 1, delta omega 2 are one and the same as delta omega. We will see that. Once these two areas are put in parallel, we are very sure that frequency deviation experienced by these two areas is delta omega given by step change in respect to area, like delta PL1 minus divided by 1 by R1 plus D1 plus 1 by R2 plus D2. That was the standard equation where D1, D2 went to 0. Therefore, it remained minus delta PL1 divided by 1 by R1 plus 1 by R2 as deviation noticed. So this works as 10 megawatt change. 10 divided by 1 divided by 0.015 plus 1 divided by 0.0015 like this, which turns out to be 0.0136 radians per second, because omega in radians per second. So now, because it is not mentioned per unit like that, everything is in fraction. That's it is working like a radians per second, because default unit of omega is radians per second. Then what is that proportionate pickup taken by the area 1, delta PM1 is by this equation minus delta omega divided by R1. You can see minus delta omega. What is delta omega? Delta omega is a drop in frequency. Already is a minus here. So originally there is a minus outside. Delta omega is again a dip here. This minus cancels off. What remains is delta omega divided by its droop R1, which makes 0.9091 megawatt compensation additional. So for a change of 10 megawatt, there is a compensation of 0.9091 megawatt from the area 1 itself. Then what is that delta P12 expected? Delta P12 expected is nothing but power among the corporation. What is delta P12? P12 means exchanging between 1 and 2. Change in load is area 1. Now who has to work for this? Area 2 has to supply now here. Just see how exactly this makes the sense here. So delta P12 is delta PM1. What is the energy situation at the area number 1? The share is only 0.9091. Yes, minus what is the actual load at area 1? Load at area 1 is 10 megawatt. The difference between them is minus 9.091 megawatt is a shortfall. Then how it is fulfilled? It must be flowing from other area only. Now let us see whether it flows from other area or ACE makes it possible. So now let's look into this. So delta P21 is equal to minus delta P12, which is 9.091 megawatt. Now let us put in the ACE equation. What is that ACE equation? The mismatch power or exchanging power plus the beta 1 into delta omega. Beta 1 here is what? 1 by R1 plus D1. D1 is 0. Hence you will find only 1 by R1 into delta omega. This K1 into delta P12. K1 is 1 here. K1 is not at all mentioned. K1 is 1. Delta P12, K1 is 1 plus beta 1, 1 by R1 plus D1. D1 is 0 into delta omega. This equation become revisited as minus 9.091, whatever the delta P12 we got from the energy balance of the area number 1, plus 1 by R1 into delta omega, which causes a 10 megawatt as an error in the area 1. Let's look into area number 2, ACE2. ACE2 is delta P21. What is delta P21? Delta P21 is exactly negative of the delta P12, which you can see here, which is a minus 9.091. It is positioned as plus 9.091, nothing but this is opposite to that, plus delta omega divided by R2, 1 by R2 into minus of 0.0136. If I work it out, it cancels this to 0. So what you get from this, there is a change in load of 10 megawatt in an area 1, even though there are two generating areas of different capacity. One is having a generation ability of 1000 meeting the load, another is having a 10,000 meeting its load, interconnected. Now the concept is, if there is a complete ALFC interconnected, how is that ACE comes into picture? This question is indirectly compelling you to explain or to present how area 1 load is addressed by area 1 itself, area 2 load is addressed by area 2 itself. The keyword ACE here compel you to show that. You shall not work like ordinary problems which you have done already. This ACE keyword compel you to show that who is responsible to take care of this 10 megawatt shift in load. For us, when ACE comes in question, the respective area experience a change means that area only need to work for that. That's what we have to show. To show that after having energy balance and after having frequency deviation, after having pickup taken by area 1, let us compute the ACE1, ACE2 using the standard equation. We will come to know who is going to respond for the 10 megawatt. So exactly 10 megawatt is responded by ACE. This ACE, if I go back to the situation over here, 10 megawatt of these two interconnected area experiences a change in load, but load is changed in area 1. Therefore, ACE of 1 only need to act on the integral controller to see to it that energy balance is again maintained by 10 megawatt drop. So therefore, you will find a minus sign here that I have put in other discussion. This minus sign indicates that ACE is having a minus means there is a shortfall of power in the area, deficit generation. Then till ACE becomes 0, integral controller keep on acting on the value of the P reference point, see to it that ACE becomes 0. Negative is to correct it as an increase in set point. Suppose other way, if I explain the problem, if 10 megawatt load suddenly dropped in area 1, what would be your observation? Just opposite to the situation. 10 megawatt load is suddenly removed in area 1. In which area load change has occurred? In area 1. And frequency definitely shoots up. Then who has to reduce the generation? Is it area 1 or area 2? Area 1 only. Then who will compel this generation? ACE 1 automatically at that become plus 10 megawatt. It means ACE plus means there is an surplus generation. Then that you have to manage. So therefore, whenever there is a shift in load in area respectively, the respective ACE will compel the controller. Negative ACE indicates that that area need to generate more. The plus ACE indicate that already there is an excess generation happening. You need to reduce the generation. That is the knowledge we get from sign convention of ACE. So therefore, here I am very clear. Minus 10 megawatt indicate you that there is a need of generation of 10 megawatt additional in area 1. That is experienced as ACE of area 1 is minus 10. So it's a very simple problem. Just about 4 lines of problem make you so much knowledgeable information in this compact presentation. So therefore, area 1 to increase the generation by 10 megawatt. The same text is put in the bottom here. You can just see. So likewise, you can experience, you can solve just by making load change 10, try by 20, try by making the group natures different. Then you will experience these equations, or these equations are helping you to compute that. In that way, we need to practice the problem. Similarly, a small change in numerical values will be the problem in the examination. Okay. Then moving to similar another area. I just go back to one more problem and come back. Let's see. Where is that area? Just a minute. I'm just moving forward. I'm trying to see one more problem which is having continuous change in that. Continuously detailed information I will get. We'll just see. Where is that? Yes. Yeah. Here. This problem. Very lengthy problem. This I think I had took from K. Umarao. Another is from Prabha Kundur, another big textbook for power system operation and control. One of the question I took from here. Consider two 50 hertz interconnected systems. The connected load is 15,000 megawatt in area 1 and 30,000 megawatt in area 2. The generations are 14,000 megawatt and 31,000 megawatt respectively. The area is having a 15,000 capacity, but right now generation is 14,000. Another area is 30,000 and its capacity of generation is 31 megawatt. D1 and R is 5% for both the areas. I think they have given D and R common. They will tell us to compute it on base of first area, base of second area. We'll see. D is 1, R is 5 for both the areas. Area 1 has spinning reserve of 1000 megawatt. See here. It is having load of 15,000 megawatt and generation was 14,000. Then this 1000 mismatch you have noticed, that is put as spinning reserve spread over the generation of 5,000. Here we have to understand a little bit carefully. This area is having 1000 floating energy extra, which is kept ready as a spare, which is shared by some generator in that area, out of which 5,000 megawatt capacity generators are only responsible for keeping spare. Remaining generators are loaded out of their capacity like that. This 1000 is spread for 5,000 megawatt generators, which are 1, 2, 3 together. Only those generators are able to deliver this 1000 megawatt is the meaning. And area 2 has spinning reserve of 1000. Area 2 is having very less spinning energy, like 1000 spread over 10,000 megawatt. So therefore, It is not that all the generator will keep a spinning energy and add to a system. It is some of the generator only generate extra and keep themselves as spare for the system. In that way, 1000 megawatt from area 2 is put only by 10,000 megawatt capacity generations. Determine the steady state frequency, generation, and load of each area, and a tie-line power for the following cases. This is a very complex situation, very typical case study on an area in a distinguished way. Let us try to understand this problem. It's sufficient because we will not be having this complete length of problem. We will be having either case 1 or a case 2. That's all. So for me, with supplementary control, without supplementary control is what I wanted to present from this problem. In that due respect, I have taken this problem taking into consideration. So areas are interconnected, having their respect to loading center and generation abilities, droop and D nature, and spinning reserve available in that area respectively, and obtain the generation, steady state frequency, and tie-line power flow for the following situation. Number 1, loss of load 1000 megawatt in area 1 with no supplementary control. See here, loss of load. Suddenly load is rejected in area 1 with no supplementary control. No supplementary control with respect to ACE as such. And loss of load 500 megawatt in area 2 with no supplementary control. It is to see how that sudden loss or sudden rejection of 1000 loads in an area is counteracted in the area 1, area 2. Like that, we need to understand by case 1, case 2. And case 3, if generation carrying spinning reserve is on supplementary control with the frequency bias setting of 250 megawatt per 0.1 hertz for area, it is called beta 1. Beta 1 for area 1 and 500 megawatt per 0.1 hertz, beta 1 for area 2. Evaluate the following. The same case study, if there is a supplementary control, without the supplementary control, how we have to work? If there is a supplementary control in area 1 and area 2, to see supplementary control with loss of 1000 megawatt, how system will cope up its operation. If the supplementary control in area 2 for a loss of 500 megawatt, how system is going to work. That is the case study in case number 3. If generation carrying spinning reserve on a supplementary control loop is situated with the frequency bias setting of 250 megawatt per 0.1 hertz in area 1 and 500 megawatt per 0.1 hertz for area 2. Evaluate the following contingencies, following situations which may occur or which may not occur. We call them as contingencies. Unexpected instances or happenings in the power system may or may not occur. Preparedness for them is the securedness of the system. So therefore, contingencies are titled in that direction. So for a first contingency, loss of 1000 megawatt in area 1. Suppose case study 1 is pulled down here with these two B1, beta 1, beta 2 there in the loop 1, loop 2. If 1000 megawatt is dropped, how the system is going to behave. Suppose 500 megawatt generation is dropped, how they are going to behave. And 1500 megawatt is reserve is not carrying, how they are going to do. Tripping of tie line without change interlay. So many cases. Let us go one by one. Let us say first case study, very simple. Loss of 1000 megawatt in area 1 with no supplementary control. Let's view the solution. Loss of 1000 megawatt in area 1 without supplementary control. For that, what I require, I need to see carefully. The values are put in percentage, correct? Now, when the droop is mentioned, how that drop in load make the frequency to shoot, how to reduce it normal. Megawatt per hertz control I have to bring into the fraction. Therefore, the R1 and R2 I need to convert from percentage to megawatt per hertz, because every drop of megawatt, what is that change in frequency, or every drop of frequency, how is that control action has to come. That is to droop only. Therefore, it is necessitating to convert this droop into megawatt per hertz representation. You can see here R%, R is 5% in both the area, we consider regulation on total capacity of each area megawatt per hertz. That means 1 by R1 I want, because 1 by R1 plus D1 is my requirement. In that due regard, what is 1 by R1? 1 by R1 is 1 divided by percentage, 0.05, 5%, 5 divided by 100 into, it is on megawatt per hertz. Then it is 15,000. It is the connected load of area 1. At what frequency it is working? 50 hertz. Means this value is transformed percentage, which is 0.05 fraction, is transformed as, by multiplying it with megawatt per hertz. 15,000 is the capacity of area 1 where I am working upon R1, and 50 hertz is the working frequency. This factor is transformed as 6,000 megawatt per hertz. So you can just imagine, if I, instead of doing 1 by R1, if you take R1 only, you can do it. It is 0.05. 0.05 into 50 divided by 15,000. That works as 6,000 megawatt per hertz. The droop of 1 by R1 is 6,000 megawatt per hertz. Similarly, R2 is also 5, but it is on base of 30,000. I mean 32,000. What is that? 32,000. How I am going to get 32,000 here? Just see here. 32,000. Here I have 15,000 megawatt connected, generation of 14,000, and spinning reserve of 1,000 there. It becomes 15,000 for me here. Here it is 31,000 megawatt and 1,000 spinning reserve spread on the remaining area. That becomes 31 plus 1, 32,000. So I'm trying to convey you how this 32,000 has come, how this 15,000 has come. 15,000 has come. The capacity of generators are right now 14,000, but how much spinning they are keeping in the system? 1,000. So 14,000 plus 1,000 become 15,000 here. Similarly, for area 2, 31,000 megawatt plus 1,000 megawatt spare on 10,000 capacity. That is 31,000 plus 1,000 become 32,000 as a capacity of the area 2. So 32,000 divided by 50, transform this into 12,800 megawatt per hertz. So these two are the requirement for controlling the 1,000 drop in area 1. So 1 by R1, 1 by R2 are the interconnected areas, the droops mentioned. Let's see how it's being done. The total capacity equal to, this equation is very interesting. So total capacity equal to generation in each area plus spinning reserve. How it is that? 14,000 is the generation taken up in area 1. Spare spinning in that area is 1,000 plus generation in area 2 is 31,000 megawatt. Its spare spinning reserve is 1,000. Together, total generation capacity of the interconnected operation is 47,000 megawatt. So regulation due to 47,000 megawatt capacity is given as 1 by R equivalent equal to 1 by R1 plus 1 by R2 plus 1 by R3, like that. That's called equivalent representation of the interconnected operation is 1 by R1 plus 1 by R2 in this case. So 1 by R1, 1 by R2 already worked out here. 1 by R1 only is 6,000. 1 by R2 is 12,800. It reminds me addition of 6,000 with the 12,800. You can see 18,800. Are you able to get 12,800 plus 6,000? It becomes 18,800 megawatt per hertz. So it is the nature how people have done the value. It is not that we have to do 1 by R1. You can keep it ready 1 R1. You can keep it ready R2. Take them in this way, 1 by R1 plus 1 by R2, which again make a shifting to the numerator and getting it to total value. Load damping due to load change of 14,000 megawatt after the loss of 1,000 megawatt in area 1. It means, so there is a D mentioned. What is the D mentioned in the area 1, area 2? 1%. D is 1. It is 1% change in every percent change of frequency. Then how it is being worked out? Load damping due to load of 14,000 megawatt after the loss of 1,000 megawatt in area 1 is load's reflection. How is that load going to respond if there is a sudden drop of 1,000 megawatt from the total connected load? Then we can say 1 by 100, 1%. into full capacity 100% to the 50 hertz of it as the value of capacity running. 14,000 divided by 50. Just see how it is being done. 14,000 divided by 50, 1 divided by 100 for its 100% capacity. So here 14,000 divided by 50 into 100 goes out here because 100% of full. These two need to be cancelled. So 1 D as a 1, just take a short form, D as a 1 into capacity divided by frequency. So these 100 you can just omit off from your picture. D into capacity divided by frequency. It becomes 14,000 divided by 50. That turns as 280 megawatt per hertz. So there is a change for every 1 hertz change. 280 megawatt is getting affected in the area. That is the value of D in this area. So this is not given. D of 1% is given. 1% of what? Whole capacity of that area. Therefore, D in terms of megawatt per change in frequency calculation stand as the total load divided by frequency into constant D. So when it is worked out as 280 megawatt per hertz, note that just a text given here. It is the 1% variation for every 1% change. The same thing I was speaking. Similarly for area 2 load damping due to load of 30 megawatt in area 2. That is 1 into 30 divided by 50. 30,000 divided by 50 into 1. So this 100 this cancels off. This is to convert them full capacity to the percent. 100 is null off here. 1 value of D into capacity in area 2 divided by frequency of operation. If I calculate, this results me 600 megawatt per hertz. So what we got now? R1 D1. Earlier we got D1 D2. Earlier we got R1 R2 in terms of megawatt per hertz, megawatt per hertz. Here we got megawatt per hertz, megawatt per hertz. Now I am in a right position to get beta 1, beta 2. What beta 1 refers to? 1 by R1 plus D1. What beta 2 refers to? 1 by R2 plus D2. To match that, these were converted into representation. So therefore, when I have D1, D2, two responses, what I can do to get the total frequency deviation, I require in the denominator load change divided by 1 by R1 plus 1 by R2 plus D1 plus D2. To represent this, 1 by R1, 1 by R2 is 1 by R equivalent, and D is D1 plus D2, simplified by the author here. So instead of writing 1 by R1 plus 1 by R2 plus D1 plus D2, D is capital D, nothing but D1 plus D2. So 280 plus 600. This is from composite response with respect to sensitive loads. D is D1 plus D2. 1 by R is 1 by R1 plus 1 by R2. 18,800 plus 880. If I take in the denominator to the PL, 1000 loss of load. You can see here the minus indicates. Earlier we had minus delta PL is the change in load positive side. Increase the load, we have seen all the problems. But in this problem, what is the load? 1000 megawatt is dropped. So inside the bracket, you will see minus 1000. So therefore, the frequency deviation is 0.050813 hertz. So you might wonder here, all the values are working on megawatt hertz. Hence frequency deviation will come as hertz only, not in PU. So therefore, all the values got worked out on megawatt and hertz only. Hence, this is 0.050813 hertz. Plus indicates that over the base frequency. What was the base frequency in this case? Base frequency was 50. When the load of 1000 megawatt is dropped, what would experience here? 50 hertz is going to rise forward by what value? 0.050813 hertz. This is the increase in frequency. Because of this increase in frequency, what will happen to the loads in area 1, area 2? Because D1 and D2 represents what? Frequency sensitive load response. It is nothing but D1, you watch here, 280 megawatt per hertz. What is the indication here? For every 1 hertz change, what is the change in power? 280 megawatt. In area 2, every 1 hertz a change. 600 megawatt is getting compelled. It's a variation of either 600 side, 600 megawatt upper side, or 600 megawatt lower side, depend on the frequency. Rise means increase, fall means decrease. You can see here. Therefore, due to change in frequency, change in load delta PL1 is D1 into delta omega delta F. This is called frequency sensitive load changes. This is 280 into this change in frequency. There is a increase of load. Now you will see XL. What is XL? 2 pi FL. Inductive loads automatically increase due to change in frequency. If frequency drops, inductive loads automatically get rejected. But in this case, you have reduced 1000 megawatt load from area 1. Then what it has reflected indirectly to you? Frequency to go up. Because of frequency shooted upward, inductive loads are drawing more power by this way because of sensitiveness to the frequency. D1 into delta F is nothing but, even though there is a drop of 1000 megawatt in the same area, what is the change in load? D1 into delta F, that is 14.226764 megawatt shift increase in the load. This is increased because of 1000 load dropped. So this is how is an invisible play of frequency sensitive loads here. Load is dropped by 1000, no doubt, but this is the growth of load due to increase in frequency. So this is how sensitivity of the loads on frequency matters here. This is the reason the control action must be so sophisticated with the primary and secondary loops only. Similarly, due to this 1000 load drop as well as change in frequency, how is that load growth occurred in the area 2? Delta PL2. Delta PL2 is again D2 into delta F. And D2 worked out as 600 megawatt per hertz into the shift in frequency deviation. If I work it out, 30.4878 megawatt. See here, together you please add it. This results you nearly 45 megawatt of load is just created additionally in the interconnected system because of 1000 megawatt drop in the load in the area 1. Area 1 rejected 1000 megawatt, got relief of 1000, but both the areas over here suffering an increase of load by 14.2 megawatt and 30.48 megawatt. So this is an unexpected change in load. This has to be taken care by the control system. Therefore, drop of 1000, rise of frequency. Rise of frequency, increase of frequency sensitive loads in both the areas. So this we cannot avoid. We have to adhere to this to see to that this is balanced. Now let's see how the change in generations have to take up in case of 1000 megawatt drop here. How is that generation in area 1, area 2 will reduce their generation respectively for 1000 decrease? Let's see here. Change in generation due to speed regulation, because governors which are going to function automatically due to this frequency deviation will get controlled. That is called as delta PG1. Change in generations at generating area 1 is minus delta omega or delta F by R1. That is nothing but 1 by R1 is already worked out as 6000 here. We have already done in the previous slide. 1 by R1 is 6000. Therefore, it is minus 6000 into shooted frequency delta F, that is called 0.050813, which indicates 304.878 megawatt. So this is the additional energy there in the generation. So therefore, I have to see what it will be done for this. Then similarly, what is that energy component Pg2 share? Pg2 share is minus 1 by R2 into delta F. When I work it out, it becomes minus 12,800 because R2 is 12,800 minus R2 into delta F, which results me minus 650.4064 megawatt. Let us see. These were the tentative generation changes in area 1, area 2 for drop of 1000 load in area 1. This is only with the primary control. Question part A was only with the primary, no supplementary control. Hence, there is a sharing in both the areas. That's how we are working PG1, PG2. Now, new generation and in each area is, in each area, suppose area 1 I consider, what was the load in area 1? 15,000. What was the actual spinning reserve available there? 1,000. I mean, what was the drop in load available? 1,000 drop. 15,000 load was there, 1,000 load was dropped, and additional load growth. What was the additional load growth? 14.22. This seen load actual after drop of 1,000 is 15,000 minus drop of 1,000 plus growth of 14.22 result you 14,014.22764 megawatt as a net load in area 1. Then what is the generation in the area balance? 14,000 was the generation. Let's see here. It was a generation 14,000. Now what is the command given here? Minus 304.878. It is to decrease the generation there. Then what is the new generation set point? 13.695. It means due to the sudden drop of 1,000 megawatt in the area 1 generator not going to reduce 1,000. They are going to reduce only 304.87 megawatt because there is no supplementary control to act one area alone. Therefore, both are controlling the 1,000 megawatt. So therefore, generation revised at area 1 is old generation minus reduction in generation, nothing but pickup which has to be reduced backward, which is 304.87. This is the new generation set point in area 1. Accordingly, in area 2, load was 30,000 original and growth additional got is 30.487. So actual load situation in area 2 stand as 30,000 what is that? 30.4878 megawatt. So here you will see there is no rejection of load in area 2. Only rejection was in the first area. Here it was 30,000 plus incremental load due to rise in frequency is added to this. So this is the new load. How this is addressed? The generation originally in the area 1 was 31,000 megawatt. Then the command to decrease was 650 megawatt. It is true that higher capacity will respond more, lower capacity will respond less. This is proportional to the capacity. So 650 megawatt was the share of area 2 for the 1,000 megawatt. Then it has to be decreased in the generation. 31,000 minus 650.4064. That is going to schedule new decreased generation. Now, from this, what we learn? Tie line flow from area 2 to area 1. What is going? Now we can see net generation area 2 is 30,349.5936 minus the total load in that area 2, 30,030.4878. Can you see this difference between generation demand? That is 319.10 megawatt is the only power has to flow towards area 1. Now the frequency of tie line operation is 50.0508. This is called 50 plus side, it has increased. This is increased, delta F is added to this. So therefore you will find the 650 megawatt what was flowing. Now it will not be going 650, it is going only 319 as a tie line power. So this problem makes you an understanding of share of load without the supplementary control. If there is a load change in area 1, this would be the case. If the change in load is in area 2, similar work you have to do. How we will be doing? So regulating characteristics on 47,000 unit capacity is still 18,800 megawatt per hertz. Then D1 calculation, D2 calculation, then effective D, add these two. Then change in system frequency due to loss of 500 megawatt, loss of 500 megawatt in area 2. Then it is delta PL2 divided by beta 1 plus beta 2. Deviation is very less compared to earlier, 0.0254 hertz. Then the growth of load in area 1 is this deviation into beta 1, deviation into D1 into delta omega, D2 into delta omega. So when I calculate, these were the additional growth in load in area 1, area 2 for a loss of 500 megawatt in area 2. Very similar steps we need to follow. Then share which has to be taken reduction in PG1, PG2, delta F by R1 minus delta F by R2 minus decrease of 152.4, decrease of 325.12 megawatt. When these two are the decreases, we have to set here. Total load was 15,000 in area 1. Growth in load was 7.62. Add this. This is the new load in the area 1. New generation is 14,000 megawatt minus decrease command here. This is decreased because 500 megawatt is reduced in area 2. Share of this area has to be taken out of the generation. 14,000 minus 152. This stand as new generation, like earlier case study. In the load area 2, 30,000 was a new old load. 500 megawatt is decreased, and 14.986 megawatt is grown due to frequency rise. Old load, rejected load, load growth. If I take, that's called load situation. Then generation. What was the generation? 31,000 was a generation megawatt, and decrease command is 325.12. So this is the new situation of load. Now tile and flow from area 2 to 1, difference of these two. If I take a difference of these two, generation minus demand, so 1159 and frequency this. So it's how this is with respect to no supplementary control. Both the areas are changing their generation, making the tile and power flow to exchange among them because of absence of supplementary loop. With the help of frequency response, beta 1, beta 2, both are striving hard to control the deviation to the nominal value 0. That is the reason tie line flow is possible. To control it, tie line frequency bias. So if it is needed, then only flow. Otherwise, each area has to work on their own area load. That is the case study with the supplementary control. So when supplementary control comes, hope I am audible to you all. Hope I am audible.
Yes, sir.
This problem requires a lot of attention. I tell you this in the book, if you see, it is spreading 4 pages. Like our old textbook, GL Kushik was another textbook. It was there. Similar problem was there. Similar in the sense, numerically different. It was spreading 4 pages. That was never asked in the exam, but part of that were asked in the exam. That is the reason this problem has to be understood at least once. Hence, I am trying to make this same problem I picked from Umar Rao and another problem from Prabha Kundur textbook, which is the one of the reference book of your listings. If supplementary control is there, how the loss of or drop of 1000 megawatt in area 1 is addressed by area 1 only, we are going to understand. That is the feature of supplementary control. Let us read the statement here. Loss of 1000 megawatt load in area 1. There is no great control is required. Just observe this. Area 1 has a generating capacity of 5000 megawatt on a supplementary control. With loss of 1000 megawatt in area 1, supplementary control act to bring ACE to 0. There is a supplementary control from the frequency deviation feeding back to the set point change using the integral controller. That controller try to make the set point change such that error, that is frequency deviation, is brought to 0. If frequency deviation is brought to 0, definitely balance in the area has come. To do that, ACE will be the stimulus. Then what is that ACE? ACE has to take care of loss of 1000 megawatt. Supplementary or decrease in generation has to come up. What is that? Likewise, the supplementary control in area 2 will bring ACE to 0, because that is not supposed to respond for the loss of 1000 megawatt in area 1. This is the additional intelligence at the first layer. Which area is suffering, that area only should respond. Other area should keep its operation quiet. That is how area 1 is experiencing a loss of 1000. Area 1 need to reduce its generation. Area 2's ACE should not compel for that. That's the meaning. ACE in area 2 should remain 0. How it is going to be remain 0? Look into this equation. ACE in 1 equal to delta P12 plus beta 1 into delta F has to become 0. Then ACE in area 2, nothing but delta P21 plus beta 2 into delta F, which is written as delta P1 P21 is minus of delta P12. You can see here. Plus beta 2 delta F equal to 0. Then delta P12 is 0 and delta F equal to 0. This means there is no steady state deviation in the frequency or Thailand power flow. So therefore, how it is being done? Whatever is the loss which is occurring 1000 megawatt, that has to be the change in ACE of that area only. Then that ACE will address that delta P12 to 0. So therefore, we have to see to that first equation turns the ACE to 0 by making its set point change equal to the shift in load. So this means that there is no steady state deviation in the frequency or Thailand power flow. Should not occur. Area 1 with the particular supplementary loop ACE1. ACE1 is what is going to act. ACE2 is should be 0. Loss of 500 megawatt. How it's going to work? Just see. Loss of 500 megawatt generation with the part of spinning reserve in area 1. So area 1 has a reserve of 1000. As it was paragraph of presentation in the problem. 1000 megawatt was spread over 5000 megawatt. It means for loss of 500 megawatt generation in area 1 only in spinning reserve area, not in the general distribution. 1000 megawatt which is spread over the 5000 megawatt capacity of generation. From that 1000 megawatt, 500 megawatt is lost, not the general load. This is the loss of capacity of generation, spinning energy, how it is being addressed. This is what we have to look into. So 1000 megawatt spread over 5000 megawatt capacity, nothing but 4000 generation and 1000 reserve. That is the total capacity. Therefore, spinning reserve lost due to loss of generation is in proportion to 500 megawatt is the loss out of 4000 into 1000 as a ratio capacity of reserve. It is nothing but 125 megawatt is the total loss. Remaining reserve 1000 minus 125 is 875. It means 500 megawatt is the loss in total proportion. Out of the total 4000 capacity, what is that proportional loss is only 125 and remaining spinning reserve is 875 megawatt. Such loss of generation is 500 megawatt. The reserve of 875 megawatt can make up for the loss of 500. So there is no change in Thailand power flow. It means 500 megawatt loss in the generation of a spinning occur. How is that 500 megawatt generation is made out of the remaining generation? If it is less than, very higher than 1000, it cannot do, because already we have 5000 generation, and you have 4000 load on that. 1000 is a floating energy. You are lost only 500. Still 500 energy is floating with you. If it is more than 1000 loss, definitely it will demand from the neighbor area. That is the meaning here. Since the loss of generation is only 500, reserve is standing with you is 875. If you would have demanded more than 875, this was not able to manage. Then Thailand power flow is necessary. That is a scene which is created here. Then like this 1000 megawatt loss, similar 1500 megawatt loss in area 1, not carrying spinning reserve. See yesterday how it's going to work. So this is going to be a typical complex situation. 1000 megawatt generation loss is made up of spinning reserve. After this, area 1 can no longer control ACE, but supplementary control in area 2 can control. So 1000 megawatt loss in area cannot fulfill the area's balance. Area 2 has to respond. So this way ACE2 will respond with the minus delta P12 plus beta 2 delta F. With this, so if I calculate beta 2 with the 500 megawatt per 0.1 hertz, which is 5000 megawatt per hertz. 0.1 I shift to the numerator. Area load damping in 1 is 1%. 1 into 15,000 divided by 50. 100 are redundant here. 1 into 15,000 divided by 50. That becomes 3000 megawatt per hertz. I'm quite sure this problem is not that easy problem. It has to be worked very carefully. Then only we were able to understand this problem. So balance of 500 megawatt generation is total loss minus spinning reserve. So this we have to manage. So loss of minus 500 D1 delta F into P12. When I calculate, I'll be able to get deviation frequency. So deviation frequency stand as lesser to the fundamental frequency, which is 49.9056. Then, because of this drop in frequency, delta F, definitely loads have reduced the capacity. T1 into delta F is the change in load. So minus 300 into this deviation is 28.302 megawatt load is decreased. See here, there is a loss of generation and there is a drop in frequency. This drop in frequency reduces the inductive loads to 28.302 megawatt lesser to the original. So like this, we need to consider this case study carefully. Then change in tie line power flow, delta P12. So this equation is coming from change in area 1 load. What is the power flow on area 2 towards 1? It is delta omega into beta 2. It is nothing but minus delta PL1 into beta 2 divided by beta 1 plus beta 2. That is the equation being used here. So this delta F contains that equation here. So that is multiplied over here and you will get this equation. So therefore, change in load of area 2 is D2 delta F. So therefore, I suggest this is there already in the textbook. Kindly go through this problem in steps by steps. Then only will be able to get the concept. So when I have this particular concept, load and generation in the both the areas stand at the end of this transaction as 15,000 megawatt load minus the drop in load, and this is 14,971. Generation was 14,000, a drop of generation by 500 megawatt, 13,500, and load in area 2 was 30,000 original, and shift down load due to frequency deviation is 56, and when I reduce it, this is the value, and generation was 31,500, 31,000 megawatt original. Due to the drop in load, there is a proportionate drop in generation also. Plus, this was the exchanged power from area 2 to 1. 2 is responding to the change of 1 by this way. So this is how this area both together hand in hand works. So this last line shows when the supplementary control in area 1 not able to cope up for the changes in its area, definitely A's of the other area respond for that. This way, when is that area 2 respond for a change in load of area 1 is controlled by area frequency bias and tie line frequency bias. That frequency is not able to cope up back to zero deviation. That time there is a synchronize between the area 2 and area 1 to share the load from area 2 towards 1, on which the frequency deviation can be brought to steady value. So this shows the last term 471.7 is the share of load from area 2 because of area 1 loss, which was seen here. There is a change. 1000 megawatt of generation loss is made up of spinning reserve after this area. One no longer control A's, but supplementary control of 2 can control the A's. Supplementary control of 2 means area 2 is going to respond for this loss, 1500 megawatt loss in area 1. Therefore, that is how, what is the control is playing? 471.7 megawatt, it is delivering towards that. This is how the share of area 2 for the area 1's demand has come here. This is nothing but tie line frequency bias. The drop of frequency on the tie line, which was not made up by supplementary control of area 1, which didn't match deviation back to controlled point. Area 2 is now responding to response for the deviation by delivering the power. So if it delivers 471.7 megawatt over the tie line, the frequency deviation brought back to 0. So this is how a simple idea, but it will complicated in steps. We have to follow very simpler one by one only. So this tripping is very similar. This is not there. Again, this concept will get diluted. I'll not go for D part of this one. Similar question I have here, which from Prabha Kundu textbook I have picked it up. This is very clear to understand. Two areas are interconnected. Load of this area, generation of this area is given. Load of this area, generation of this is given. D of this total areas, one is the D here, D here. R is 5%, 5% here. power exchange among the corporation is 1000 megawatt is given as that graphically he has given, and it is narrated here. How the scene is mentioned. See the problem depth only. Problem itself is very lengthy. Connected between these two by 60 hertz is an American continent problem by Prabha Kundu textbook. Okay. How a loss of 1000 megawatt or whatever the similar scenario is explained, put over here. Can you see this problem? So there are 5 case studies similar to the problem we had discussed in the K. Umarov textbook. It is there. It is a similar problem. K. Umarov textbook is having a 50 hertz representation and capacities where it will be different, but it is the original problem in the Prabha Kundu textbook. So I suggest you please go through this problem also. Whatever I have done a discussion, similar calculations you will find. So when we keep 1 by R1 equal to 1 divided by 0.05 into 100 by 50 into capacity by 100. 100 was redundant, I said 100 is taken out here. You can see this. Some simple steps in this Prabha Kundu textbook. So this way, the similar calculations, whatever were mentioned, were put here. You can see it look little simpler. The work calculation for this problem, this is the similar problem. What we have taken here, very similar problem. This is very complex in statement itself, but here it looks little lucid. Problem, clear terms, and clearly mentioned step-by-step solution. Step 1, step 2, again summary, again next case study, summary, next case study, summary, next case study, summary. Can you see this? This is so lengthy, about 6 pages it will come. So such problem we will not get in the exam, but outcome of that is 1 or 2 of such cases will be there in your exam of worth 10 marks. Therefore, I suggest all of you to please go through this problem, which looks little comfortable to follow, but it is of 60 hertz. No